Welcome, data people. We are Zuma. My name is Matt, and this is the Data for Good podcast. This podcast is brought to you by Zuma. Zuma is a dedicated recruitment company focusing on data positions across Berlin. The Data for Good podcast is for the world of data science, analytics, and engineering, giving you a platform to hear the thoughts and opinions of data leaders from Berlin and beyond. Today, we are joined by Dmitry Yanter, VP at Deutsche Bank. Dmitry, welcome. How are you?
Hi, Matt. Hi, I'm good. Thank you. And you?
Very, very well. Thank you. Very well. For the listeners who don't know who you are, a quick introduction would be fantastic.
Yeah, thanks, Matt. So, brief intro of myself. I work in Deutsche Bank for maybe 10 more years, and overall, I spent maybe 15 years in technology, starting from startups and now working in, as many people will say, like established enterprise environment. So really very interested to share experience that we see in finance world, and that might be really helpful and useful for other people in this overall data science data area.
Absolutely. Coming from Deutsche Bank, of course, we'd have to ask you about finance, and you're going to give us some rich insights. And in particular, today we're going to talk about financial modeling and how we can use this to help and support the ever-growing data science world. So a quick intro into financial modeling for those who don't know. What is it in simple terms?
Well, in simple terms, financial models help you to understand how market behaves. So it helps you to understand how you best deal with your trades and portfolio of trades, which is a combination of everything that you have on your books. And in terms of history, I would say it's quite rich, again, compared to data science. So first models appeared more than 100 years ago, and really super well-established models appeared in 1970s. So this is a very famous Black-Scholes model that had a Nobel Prize, and actually that really transformed finance world and the way we think about financial risk. So that was probably the starting point. But now I would say we have quite established theory of how we deal with markets, how we model them, and we already have quite many changes in the area. And I think practices that we have to develop during last maybe 30 years or so, they might be really interesting for other people to understand. And maybe this can be kind of a proxy for data science world, how it can develop maybe further in the next 5 or 10 years.
Yeah, it's an area that's going strength to strength within data science, of course. So how can we use these established kind of industry-wide practices in finance to support our data science projects over the next 5-10 years?
So I would maybe just go a bit into the history and to understand how basically it developed. So again, you have a very established mathematical models for this, but now you try to put them into real life. Mm-hmm. And when it comes to real life, so basically you can imagine quite significant and quite big organization like a bank or maybe a hedge fund, and they try to assess their portfolio. So they might have millions of trades or maybe hundreds of millions of trades, and they would like to understand what risk they take with them and how basically to manage it. So on the one hand side, you have something that is written in this book, like proven, absolutely accurate. On the other hand side, you have very real life thing, with sometimes it might has just errors in the data. You have to work with it not just as a one-off exercise, like one-off, I would like to understand where I am in the whole, let's say, in the whole market, but I would like really to build the way that I can deploy different approaches to understand my portfolio. I would like to develop my models as market develops. So obviously markets that used to be, 30 years ago, and now they are a bit different. They might be not different fundamentally, but there are different features that you would like basically to reflect on your models. And you have actually, if you think about it, you have to build a chain of models that started maybe 40 years ago from something that was really written in the book, in the textbook, to something that's absolutely modern and that has to reflect what's really happening in the world.
Okay, so to work with the model risk that you're talking about and to implement this process of sustainable model changes, tell us more a little bit about that.
Yeah, indeed. So I think sustainable here is really a good word. So you think about an unbreakable change of your understanding of in the environment you're working with. So, and if you just look into this very technically, then again, you might have a paper from well-known mathematicians. Then you have to put it into production, actually, where this model really calculates your portfolio, analyzes your risk, and produce meaningful results. And then you have to build on top of this model additional features, but you would like to, first of all, to ensure that you do not produce some false positive results. You would like to ensure that the way that you looked into your risk like 10 years ago is something consistent with what you see at the moment, which actually put us in a, I would say, completely different situation, not just maybe invent or describe your particular market segment, but really to build, I would say, the whole infrastructure and system that allows you to implement sustainable models, that you have your back tests, that you have your controlled framework where you understand where, for instance, your model lays between your parameters, whether it's expected or not expected, whether it's a problem of implementation or something really changed in your portfolio or in the environment. So itself, I would say, is a completely different process from what might be considered as really this naive understanding of modeling. Like, I have a problem. Let's get to it. Let's build. I don't know. Let's bootstrap some super good algorithm and let's solve it. So the thing is that you have to solve it every day, multiple times. You have to change it, and you have to prove that it's really consistent. And at some point, maybe like 20 years ago, you had to prove it only for yourself, just to be ensured that you are in line with the reality, I would say, with the markets. But now you also have to prove it not for yourself, but for regulators. So there is already a regulation for financial and model risk that you have to follow. Actually, they give you a set of rules that you just have to implement and have to prove it. So that's kind of, that's completely different thinking. So it's not just like I am putting I'm implementing a particular approach to solve my particular business problem, but I have to do it really in the right way. So I think that's really might where we might think about the data world that might lead to. So probably we have somehow to agree on the methodology that produces sustainable models and produce sustainable results. And I think that's really a key. That's really key for us, for people who work on technology side, and I think that's a key for stakeholders. So obviously they would like to get sustainable results and some kind of predictable results.
What challenges present themselves when we're not focusing on sustainability in our models? What issues would we have?
Well, first of all, again, if we just take some historical view, you just probably, on the one hand side, you just can miss some opportunity. And in finance, it's really very obvious. So you have an immediate feedback. So if you just make it wrong, you just experience money losses, like as easy as that. If you are right, then you can prove and you can provide more efficient service. And this is the feedback loop is quite fast, I would say, on the one hand side. On the other hand side, you have a very high cost of an error. And this is actually, I think, we have, let's say, another story to tell. When maybe 20 years ago, 15 years ago, we saw an increase in algorithmic trading.
Yeah.
So when people started to develop something ad hoc algorithm to execute electronically on the platforms, actually we saw quite a few, maybe not quite a few, but some very significant errors that came from technology, but impacted the market as a whole. So there were some famous incident like night trading. So that one company deployed into production. So they considered production as a stress test environment, and they actually tried to make a stress test, and they really make a stress test of the whole market, which actually leads, on the one hand side, company almost they almost put it to bankrupt, and they had to ask for money. But on the other hand side, like real people or people on the market who didn't think that it's just just a stress test, they basically had a negative impact. So market experienced significant volatility, and actually this error of one particular participant impacted others, which resulted at the end in regulation of how you basically you manage your algorithmic trading platforms. And again, you have your model, which basically allows you, on the one hand side, to automate some of your manual work, to automate some hedging algorithm. But on the other hand side, it can impact not just you as a participant of the market, but the whole market itself. And this basically where regulators again came with the message that you have to follow some rules for algorithmic trading. And then again, we started from more or less kind of more or less greenfield risk models, and they ended up with regulations, algorithmic trading, and those ended up with regulations. Again, maybe a bit unrelated field, but they ended up with some rules that market participants have to follow.
Okay, so risk calculations, electronic trading, they need to stay very close, not only for individual, but for the market as well. And that's where the regulators have come in to make sure there's no foul play, it sounds. Have I got that correct?
Well, I would say so. The thing is that at some point in time, these areas become quite sophisticated. And you cannot just simply look into anything and clearly say whether it's right or wrong. So you have to, again, really not just make an expert judgment whether it's whether it describes, your risk, your market segment well enough, but you really need to prove it as a number of tests, which makes the whole process not so flexible, but more sustainable. And why we have to follow this in a more sustainable way? Because just like an error, because think about like an error in formula may impact you as a person on the market. So, which is kind of strange, right? So it's kind of just somebody makes an error, but impacts other who actually have, and they have nothing to deal with it. It's just just the fact that you have super efficient market and they are super interconnected.
So are we aiming for more robust models as opposed to flexible models?
We are aiming to, I would say, more. And actually, that's a good point. So we are moving to more, I would say, robust environment. So you might not have. So you might have, like, let's say, quite an experimental model, but you have to define very well where it can operate. It should have very well set limits. It can operate within those limits, but it cannot hit upper bound or lower bound. If it goes up or below, you just have to terminate automatically. And that's kind of frameworks that I would say most of market participants have. So you have your algos that operate with some limits, and actually if these algos hit any of the limits, they will be automatically stopped. So it's kind of flexible, but within the controlled framework.
So how can these robust models, how can they be used in kind of mission critical tasks like risk calculations or electronic trading?
So again, you need to think about this algorithm as something that operates on the one hand side fully automatically. On the other hand side, it operates with the real life data and works like 24 hours by 6 days per week. So again, you will be in position to understand the overall output, but sometimes it will take you days to understand a particular calculation. Which, for instance, if you put yourself on the place of stakeholder, you really trust the calculation, and you really need to trust how it works. And that's, I think, one of common challenges if we speak about data science. So you have something mined from the data you have, and you have some output like telling you that you should operate a business in this way, but trust doesn't come for free, right? So you need to somehow to prove it. You need somehow to explain it. And that's actually one of the dimensions that I see some interest in finance in this explainable AI, where it's not just like a super black box, but something that you can articulate how it's built, and you can articulate your principles. And these principles, and in world of financial models, these are conditions of the conditions where you can apply this or that logic. They are super critical. They're super critical because you understand your case, and you can operate within these limits. If you have to move from one market to the other, if market conditions change, then you have to adapt. And how you have to adapt? You have to adapt somehow sustainable. You have to prove that these results that you received in situation A are in line with situation B, and you can make the bridge between those two. So that sometimes may really sounds like a bit of art, but in fact, just like quite big amount of work. And if we speak about financial institutions and big banks, you have quite a big departments, people that are, on the one hand side, they are in technology. On the other hand side, they understand the mechanics and the mathematics of the model. And basically, they have to work together, and they have to build platforms that support these changes. And you have to understand, mathematics behind it, and you have to understand your boundary conditions. So that might be really a challenge when you come up with like super generic model that you somehow bootstrapped out of 2-3 more or less standard approaches, just put them together. Sometimes you don't really understand the mechanics inside it, and that might be your weak point, because if it breaks, you don't really tell what was the problem, whether the problem is in the changed conditions, or the problem is how you describe it and how you how basically you build your algorithm.
And how would we find out which it was? Was it the environment or was it the model?
So there are, I would say, there are a few ways to address it. So first of all is you can make your, I would say just quality checks. Quality checks. So they might be quite synthetic, but I don't know. Let's just imagine that we would like to. It will be absolutely ridiculous, but let's imagine that we would like to predict how long the day is, like how many hours is in the day. So like some check that sounds reasonable. That, for instance, in the day it's you have, I know, you might have 20 hours in the day, 24 hours in the day, 30 hours a day, but maybe not more than 50 hours a day. Or for sure, you should have in the day fewer hours than in the month. So sometimes you just understand how your different parameters of the model should be. Like something should be more than, like parameter A should be more than parameter B, output parameter. So you kind of understand that at least it's not controversial. Then you might have your synthetic tests that actually, for instance, and again, that's I would say quite common in the industry, that for instance, you take your trading day, and you just simulate all models should pass this trading day, and you kind of understand what are the different outputs and whether these outputs are in line with the parameters that we really observed during the trading day. So like one is just qualitative check, the other is just the synthetic test that you really have to follow, and the other one, which is a bit more complicated, is when you make an incremental change, you should see expected change in the output result. So something that in mathematical world we'll call like stable change, right? So for instance, you add some feature on top and you understand that your output results should be fundamentally different. So you shouldn't really with additional features or with additional assumptions plug in instability of the output results. So like model A, model B, and they somehow in line. They might be not exactly the same. They should be different, but they should be in line. Should be somehow laying in the same area.
Okay, awesome. Now, thanks for sharing that to help me understand as well. A point that we've discussed previously is false positive results and how frequent access to data can produce this. So tell us a little bit more about that. What are the problems with false positive results?
So this is something that I'm really glad to share, because I think this is something that you would really should know in this data world. So again, in finance, you can find quite a few papers with strategies, with, let's say, investment strategy, and they like more or less structure the following: like you can implement this strategy and you can earn more than the market. So how they are normally built in these days. So you have your market prices of different stocks, bonds, whatever. You somehow combine them together and make kind of an artificial portfolio that performs better than the market. So kind of, I would say, quite obvious approach, but quite naive. And why it's naive? So interesting about finance, that you work with data sets that are mostly publicly available when you try to implement your portfolio strategy. So like everybody can get access to any kind of share price. It might be not like super precise, but at least you can get the idea. And then what actually happened? So we have quite a few papers where they say like, we have mined, let's say, this strategy, it's profitable, but if you would like to replicate it, then you'll fail.
Yeah.
And the question is like, why it's happening? So there are actually fundamentally two reasons as many researchers consider. So first reason is sometimes that anomalies in the market, they are super short-living. So for instance, you might have a particular opportunity, your portfolio can perform better than the market only for a week, sometimes only for a few hours. And then it just disappears. So market is super efficient, and these anomalies, they are super short-living. That's kind of, I would say, a valid reason you cannot reproduce, because this is super short-living.
Yeah.
Another thing is that actually puts us into this the so-called false positive strategy theorem, which is a bit, I would say, mind-blowing. So imagine you have your portfolio performance measure is called Sharpe ratio, where it's just a fraction of your return over your risk. So the better, normally the better it is, the better the better you manage the portfolio, kind of like.
Okay.
So there is a theorem that actually proves the fact that the more time you get access to the data, the better is an estimation for this Sharpe ratio. So it's not about, I would say, how you built, how you created this investment strategy, but just due to the fact that you get access to the data and you tend to overfit your model. And this actually produces false results. This produces false results just from overfitting.
So too much data.
Too much access to the data.
Too much access. Okay.
So again, you can think about it. So because you can think about just more or less, you have all your market indicators, and you try to combine them in the way that they seems to produce like super good results. And in fact, if you tend to get access to the data like hundreds and millions of times, you tend to overfit just due to the fact that just basically to this based on the theorem. And it's interesting that there is just there is a formula that gives you this indication how basically it tends to overfit. And this is where some researchers, they basically put it into the way how they assess their strategy. So basically they understand. So for instance, I come up with a like super bright idea, how to make portfolio better than the market. Then I bring it to them. They check how many times I get access to the data, and then they basically understand what is my expected Sharpe ratio, just based on the fact that I had 10 times or 10,000 times get access to the data, and what is my real results. And if my real results is below this maximum expected Sharpe ratio, that it's likely that's just an overfitting.
So how can we learn from this? How can we improve off the back of these research papers?
Well, that's actually quite tough question, and it's tough in two aspects. One is that it becomes you have to deploy quite sophisticated strategies. You have to really control how you get access to the data, whether you have good enough number of out of samples tests. And again, in finance, it might be, so you might test something for 10 years up to today, but obviously you don't have out of samples. You don't have, so if you want to get another 10 years, obviously you have to wait another 10 years. And so it doesn't really work. So you have to really control this amount of out of sample tests.
Yeah.
That's point number one. And point number two is I would say sometimes it's even more sophisticated to understand. But again, if I'm just reading some of these papers, so they give a very interesting idea. So data gives you an insight what you can formally prove. Just think about it. So
yeah,
you just explore the market, you explore how it works, you find some interesting effect, and then you try to prove it formally and mathematically. This is kind of super hard, to be honest, to do.
yeah,
But actually, if you find something that is really in this shape, that first of all, you can explain it, not just like I checked it and in my data set it works, but I can really somehow prove it. That's I would say a result of different quality. That's one thing. And the other thing is that I really understand how access to the data may impact my result. So it can just I really manage this. So in this finance world, we manage this model risk, and in data world, actually have to manage your risk of overfit. It's also kind of model risk, but it's really comes to, from the nature of this area. So it's kind of interesting story. So on the one hand side, data empowers you. On the other hand side, it may lead you to just to wrong results.
It's I think we could probably go deeper into this for many hours. I think it's a super interesting topic that data can help, data can hinder, and this is one of the examples of that. Now, one topic that we'd like to close with, your view on data science with data and finance, and the kind of challenges that we have in adopting some of the techniques. And
okay, so so what I see maybe what I see recently is that in finance we kind of accept the fact that you have to deploy this modern technique, AI, and data-driven model. So you have to somehow adopt, and it's not already something that could make positive impact, but something that already worked for quite a few participants. Again, you might argue that, for instance, what can work for hedge fund may not work for some other participant. But the fact is that on the market, you have players who deploy these data-driven models, and they're quite successful. So it's kind of the fact. So you cannot really challenge it and say that this is something that will not fit for purpose in this area. So it will fit for purpose. The most challenging bit is how basically you incorporate specifics of the area into the modeling, and this is really where you have to deploy and have to deploy models that are, I would say, tuned for finance applications. They are tuned for finance application, and they are not tuned just in the fact that you put finance data into them, but they are tuned to the fact that you kind of understand how they work, and their mechanics is in line with what we know already about the market. So this is a combination where you have to incorporate knowledge from the industry into math that sits behind what you apply, and that's actually, I would say that's actually a challenge. But this challenge, I think it's being resolved, because if I look back maybe 10 years ago, most people do not consider ML seriously. They just said that we have like our well-known Nobel Prize winners models from the book. We can work with them. We have super solid mathematics behind them.
Yeah.
Well, but actually it changed, and you cannot just simply ignore it. And I think it's really important for people who work in this area, on the one hand side, to understand the challenge in finance. Like, we don't have super big amount of out of sample data. Sometimes we cannot reproduce markets. Then you have a super significant cost of failure, and sometimes you cannot make particular failures. So it's I would say it has its own nuances, but I would say there are people who really work into this direction, and at least narrative has changed. It's for sure.
Absolutely. I think it's exciting times ahead. Unfortunately, that's all we have time for today. I want to say thank you very, very much, Dmitry, for your time and your rich insights. I hope you enjoyed today.
Yep. Thank you, Matt. Thanks. Thank you.
Perfect. And to the listeners, as always, drop any questions and feedback in the comments section. And don't forget to like and share so we can reach as many people as possible. But for today, it's bye from us. Thanks once again, Dmitry.
Thank you, Matt. Thanks.
Ciao, ciao.
Ciao, ciao.